let's see what frequency response is. Yeah. So before we go into what a frequency response of a system is, we need to see what are the different things that characterize a sine wave. Yeah, any sine wave or any sinusoidal oscillation would have three properties, would have three defining characteristics. Yeah? It has an amplitude. Yeah, that is how loud a signal is. It has a frequency, which is the pitch of the signal, and it has a phase, which means that how so when does the signal really start appearing? Yeah, so when does the signal really start appearing? So how much shifted a signal is, how much shifted a sine wave is from the 0 to time instant. Yeah, that kind of gives you the phase delay in the system. So these three properties, yeah, are very critical when we look at. They kind of define a sine wave. So if you see this, you have the wavelength, and which kind of is like another, it's like a proxy for the frequency. You have the voltage, which is a amplitude, yeah, and you have a phase. You see the two signals here they have a phase shift of 90 degrees between each other. Yeah. So this is so this kind of defines what a sine wave, these three properties together define a sine wave. Yeah. So this becomes very important because when we are studying the frequency response of a system, we are essentially studying what happens, how the system responds to a sine wave. Yeah. So a very important property that one should know is that any linear system, yeah, even if it's not time invariant, any linear system, if you give a sine wave to a linear system, yeah, the output of the linear system would be another sine wave which has exactly the same frequency as the input sine wave. Yeah, I repeat this. Suppose I give a sine wave as an input to a system. The output of that system, the output of a linear time invariant system, would be a sine wave of the same frequency. Yeah. So which means that the system does not change the second quality that you have here, which is the frequency. The other two qualities, of course, can change. The other two characteristics of the sine wave does change at the output. Yeah, its amplitude can vary, which would mean that you can have the signal being magnified. Yeah. So which would mean that you can imagine it this way, that suppose I have a sound of a certain pitch that enters a linear time invariant system, the output would have the same pitch. Yeah. But it can be louder at the output. Yeah. Second, its phase would change. That means you may probably start listening to the sound a little later. You may have a delay. Yeah. That's so these two things can happen, but yeah. So yeah, you have a so any linear time invariant system, it essentially changes the amplitude and phase of the sine wave, but it keeps the frequency exactly the same. Yeah. So I hope this is clear.
Okay. Sri, one second. A small general, maybe since we have just about 12 participants roughly. If there are any questions, I would request either post it on the chat window, or you can maybe just unmute yourself and ask in general. Because like I think we are just stepping up the it's a natural sequence and a flow which Srini is building up. So what's the question? It's SINE, sine wave. It's SINE, not sine. SIGN is a different thing, and SINE is how the sine wave is pronounced or written as. Yeah. Yeah. Okay. Srini, please continue.
Yeah. So so once you've seen what a sine wave is, so related to that is what's a Fourier series or a Fourier transform of a signal. Yeah. So Fourier was a 15th century mathematician. Yeah, and he was doing this stuff before the existence of transistors, before the existence of any signal processing system that we currently know. So he was fiddling around with strings. He was taking strings and making those strings vibrate, and kind of seeing what. So he was kind of seeing what you can do with these strings to get different outputs. Yeah. To what happens. So how do systems respond to various inputs and to various. So he would see how the vibration of strings would change when he changes various parameters of the string, something like tuning a violin. Yeah. So So when he was studying vibrations of strings, he kind of built this theory of Fourier series and transforms. So Fourier's theorem in mathematics was that any periodic signal, any periodic signal can be seen as a sum of sine waves, having the same sum of sine waves, having sine waves the same frequency of the periodic signal, having the same period as the particular periodic signal, and all its harmonics. So what do you mean by a harmonic? A harmonic of a signal of frequency f are signals of frequency 2f, 3f, and so on. Wherein the frequencies kind of become integral multiples of the original frequency. So it says that suppose I have a square wave. Suppose I have a square wave that that has a period of 2 seconds. Suppose I have a square wave of period of 2 seconds. Now the square wave having a period of 2 seconds can be seen as a summation of a sine wave having a period of 2 seconds plus a sine wave having a period of plus some magnified version of a sine wave having a period of 1 second plus a sine wave having a period of 0.5 seconds, then 0.25 seconds, 0.125 seconds, and so on. So it can be seen as the summation of a sine wave of the same frequency and summation of sine waves of higher of all the harmonics of that base frequency. So is there anyone here who does not understand the concept of a harmonic? Is the concept of a harmonic clear to everyone? Fine. I'll then continue. So so this is what Fourier essentially said. So why this becomes very important is that I can break down any signal into a sum of sine waves. And since we are dealing with linear time invariant systems, the sum of sine waves, I can deal with each sine wave separately. And I know that if my input is a certain sum of sine waves, and I know how the system responds to each possible sine wave, then I can for any other periodic signal, I can completely recreate what the output is. So the Fourier series kind of helps you analyze the system for periodic signals. So whenever you want to analyze any periodic signal, all that you need to know is you need to see how the system responds to a set of sine waves. A sine wave of the same frequency and sine waves of integral frequencies having which are integral multiples of the base frequency. So if I just look at how the system responds to a set of sine waves, I know how any periodic signal of that particular frequency will be dealt with by that system. So that's what a Fourier series is. So these are just the formulae and kind of stuff for that. So as you see here, so what I mean by a cos is nothing but a sine wave which is phase shifted by 90 degrees. So so this first term here, A, kind of gives you the average value of the signal. It literally is the average value of the signal. And the rest of them, the A and B and terms, kind of give you terms that are phase shifted by 90 degrees and phase shifted by 0 degrees. So what the Fourier series essentially tells you is that any periodic signal can be seen as a summation of discrete sine waves. And as I told you, since it's a linear time invariant system, suppose my input is a sum of certain sine waves, the corresponding output would also be the sum of the responses to those sine waves. And as we just saw in the previous slide, if it's a linear time invariant system, a sine wave at the input will give you another sine wave at the output, which has the same frequency, which means the same pitch to here, but it will be amplified by a different amount, and it will be phase shifted by a different amount, which means the delay and the delay and the loudness might change, but the frequency, the pitch would remain exactly the same. Now, what's a Fourier transform? A Fourier transform is like an extension of the Fourier series. So now we are not dealing with periodic signals anymore. We're just dealing with any kind of signal. So he says that any signals, so long as they are finite signals, so long as they satisfy certain properties that most signals do satisfy. It says that these signals should not go to infinity, or they should not be infinitely loud, or they should not be there should be nothing that's abnormal about them.
Srini, you want to handle this question? I think it's a relevant question to this discussion. So Shritesh has asked a question. Shritesh, do you want to unmute yourself and ask the question directly, since maybe it's a long question?
Oh, yeah. I mean, in the case of Fourier series and transforms, it goes from minus infinity to plus infinity. So in reality, is there a window that it's being used to calculate, or is there like a calculation frequency or something that it's looking at?
Generally, what happens is that suppose you're talking about audio signals, yeah. Then audio signals by nature, the sensing device itself can detect only a set of frequencies. Yeah. So we need to be bothered only about the range of frequencies which we can hear. Yeah. Similarly, every system has a certain range of frequencies that are applicable to that system. Yeah. And we then just look at the frequency response for those particular components, because the assumption is that the other components would either have zero at the input itself, or the device that's going to hear or sense that thing will anyway attenuate it to a very low value. So typically, practically, you'll just be looking at ranges of frequencies. Yeah, you'll be looking at a window of the frequency response. You'll not be looking at the whole frequency response.
Right. And so this window can be is usually defined beforehand, right? I mean, I would assume that the minus infinity to plus infinity is for the u value, which in case of audio would be related to time. Isn't that e raised to I 2 pi ft kind of a thing?
Yeah, but so the minus infinity to plus infinity here is for the frequency. It's for the value of it's for the value of the u value that you have here. That's essentially what will keep changing. Yeah. So so your u would be going from so u here is time. So your x value that you have here would be going from plus infinity to minus infinity. Your u value would be going from plus infinity to minus infinity. So what you're doing is you're taking this integral with respect to time, but what you're expressing it as is a summation of different sine waves. So if I look at the signal e raised to minus I 2 pi mu x, this is nothing but it's like a summation of a cos and a sine wave. Yeah, it's like a phase shifted sine wave. If you're looking at the imaginary number just as a phase shift, it's like a phase shifted sine wave. Yeah. So you're looking at so you're kind of so any signal can be seen as a summation of sine waves, just that now your frequency goes from minus infinity to infinity. Yeah. So your u here, yeah. So this is like the inverse Fourier transform. The f of u is nothing but the frequency response. So it's like the it's like the response that a certain sine wave would have. So what it says is that any signal can be written as as a summation. So this integral can be seen as a summation on limits, can be seen as a summation of various sine waves that have all possible frequencies. Yeah. So this u is like the frequency, and this u goes from minus infinity to infinity. Yeah. So your the range of frequency goes from minus infinity to infinity. That's your frequency changes from minus infinity to infinity.
Right. So when it comes to audio systems, we would be dealing for that within the Nyquist band, I would assume, right?
Yes, you'll be listening within the audible band is what you'd be concerned about, I guess.
Yeah.
So similarly, for for say your electromagnetic signals. So what you have with your mobile, you'll be more bothered about what happens in the microwave range.
Right.
Yeah.
Thanks.
Yeah. So if you observe this thing carefully, it's like this f of u is nothing but what happens if you give a sine wave of that particular frequency. If I give a sine wave of that particular frequency, this f of u kind of defines the gain of that particular sine wave. Yeah. So so this frequency response has two components. So this plot of f of u, is like a so f of u is like an imaginary number, which has a real component and an imaginary component. So this real and imaginary component is essentially done in order to represent the phase shift of the signal. Yeah, the magnitude of the output would be the magnitude of f of u, which would be nothing but the square root of the sum of squares of the real and imaginary parts. and the phase angle would be nothing but the tan inverse of the imaginary part divided by the real part. Yeah. So the important thing here is that when you give a sine wave as an input to the system, yeah, that sine wave would have a certain. So suppose I want to practically find out the Fourier transform of a system. What will I do? I'll take the system. I'll take a signal generator and I'll keep generating sine waves of different frequencies and giving it as an input to the system. Yeah. At the output, since the system is a linear time invariant system, the output will also be a sine wave of the same frequency. Yeah. Now what I'll do is I'll measure two things. I'll see how much that signal has got amplified. Yeah. The amount by which the signals got amplified is going to be the magnitude of f of u. Yeah. And I'll see how much phase shift is there in the signal. Yeah. So that would be the phase of f of u. That will be this phi of u that you can see here at the bottom of the screen. Yeah. So for every sine wave, I'll kind of see what the response is, the magnification as well as the phase shift. Yeah. And I'll plot this on a graph. Yeah. So this graph is like the frequency response of the system. So the frequency response of the system is like the Fourier transform of the impulse response of the system. Yeah. So we've already seen what an impulse response is. So so in order to define a system, we've got to see what happens when you pass different sine waves through. Now, why does that become so? Why is the Fourier transform therefore very important? Because it says that any signal can be expressed as a summation of sine waves. Yeah. So the basic thing about Fourier series and transforms is it says that every signal can be expressed as a summation of sine waves. Therefore, it's good enough if we study what the response of the system would be to various sine waves. Yeah. So sine waves are nothing but signals that have a single pitch. Yeah. So so since every signal can be broken down into sine waves, you can it's good enough if we just study the response of the system to these sine waves. Yeah. And that's why Fourier transforms and Fourier series become extremely important. Okay. So what you have here is, suppose I just have a square wave, the magnitude response of the square wave is going to appear something like this, which means that if you take a square wave, the square wave will have it has you have some amplitude at zero frequency, then you have this is a this kind of tells you the magnitude response for various frequencies. Yeah, so this gives you the suppose I take this as a signal, the Fourier transform of the square wave is precisely this signal that you see down there. Yeah. So are these concepts of Fourier series and transforms clear to the audience?
I believe so.
Yeah. So I'll go on. Yeah. So now any
Srini, one second. If there are any questions at this point in time, maybe if someone has a question, they can unmute themselves and ask to Srini. Else, he'll continue. So I'll maybe just give a pause of about 15 seconds. If anyone has a question, they can unmute themselves and ask Srini. It could be related to this topic, or it could be something in general also related to these concepts which he has explained. If there's any doubt, feel free to unmute yourself and ask.
Srini, can I explain the last slide again, please? The square wave and
the previous slide.
Yeah, previous slide.
Yeah.
Yeah. What is the square wave? I understand. The one below is what? Is a part of the square wave. I mean, one particular frequency of the square wave.
So if I look at like the Fourier transform square wave, so it tells you what components of which frequency are there in the square wave.
So the bottom plot is essentially the frequency response of the top plot. Yeah. The top one is the time. The top one is basically a plot against time. The bottom one is the plot against frequency.
Oh, really? Actually, I mean, practically when I look at a square wave, and if what I believe, like, square wave consists of, a lot of frequencies, like, which are almost flat. Is that correct?
A square
multiple
wave
frequencies.
Something like this. So what would be flat would be an impulse. So what happens here is, so you see a square wave now has this time interval minus t1 to t1. Yeah. So here, if you see then it is minus pi by t1 to pi by t1. Right?
Yeah.
The gap here. So this kind of goes in, this is kind of the inverse of the time that you have on top. So the intersection
Sure.
of the frequency response with the x-axis is kind of the inverse of the intersection of the time response with the x-axis with time. Yeah. So now what
So
happens
suppose
is
tell me.
so as you keep making this narrower and narrower, as you keep reducing this T1, yeah,
Then the
this will
frequency become wider and wider.
become wider and wider. So at the limiting point where square wave becomes an impulse,
Okay.
the impulse has a flat frequency response.
Yeah.
Yeah.
Okay.
The flat frequency response. But for every other square wave, it will have this kind of a frequency response. It will have this
Okay, understand. Okay, understand.
decaying kind
So
of
for
frequency.
example, like from my experience or the way I play with, like if I take a 100 hertz square wave, a 100 hertz square wave, and I can get a full audio bandwidth within that.
Suppose you take a 100 hertz square wave. Yeah. So what you will then have, on the frequency responses, you will have once. So you will have so the moment you have a periodic signal on top, your frequency response will no longer be continuous. You will have a discrete frequency response.
Okay. All right. Okay.
Yeah. The moment you have a periodic signal, because if you have a periodic signal, you're looking at the Fourier series.
Oh, okay. Understand.
Then
I got it.
Yeah, the only frequency components you will get is of that particular frequency and all the harmonics. That is double the frequency.
Okay.
So on.
Okay.
Yeah.
Okay. Got it. Yeah. Thank you.
Yeah. So
Thanks.
have a discrete kind of version of this.
Okay. Got it.